Assalamu alaikum warahmatullah. Now let us consider the general case of moving average filters. So here if we take the moving average filter as a discretized system, so it has this simple form, right? We sum a set of m points and then we divide by their number, so we're taking their average. Okay, the impulse response in this case here is very simple. It is this form, right? So we have a shifted train of deltas divided by the number of deltas here, right? Or we can put it in a what they call it a boxcar form. So if you look at the response plot, so it's like this, right? You have n points from 0 to m minus 1. So you have m points here. Okay, looks like a box. So here you have zeros and zeros. Okay, so let's investigate or study the filter, the moving average, or MA for short, frequency response. Okay, so here what we have is this. So as usual we take the Z transform of equation 3.48 and we get equation 3.50, which is again sum of powers of Z to the power minus 1, okay, divided by m. Right, in this form we cannot say much about the frequency response, or before that the transfer function. We can use the binomial expansion to simplify the expression like this, and we notice that the binomial expansion of 1 minus z to the minus m equals the first order factor and the term that we want to study. So we can redefine the Z transform into definition in equation 3.52, right here. But recall that this is an FAIR filter, right? Finite impulse response filter. This might look like an infinite impulse response filter, but it is not actually, right? So the trick is what if you substitute for the numerator by equation 3.51, you get this first order term in the numerator and denominator, and they cancel out, and you are left by the term in equation 3.50. So return back to an FAIR filter. So it's not an IRR filter. It might look like it, but actually it is not. Okay, now we are interested in the locations of the zeros of the FAIR filter. So the zeros are the zeros of the numerator. So we want to find the solution for this equation, z to the power minus m equals 1, right? So naturally z should not exceed 1 or should not be less than 1. So z is constrained in the unit circle. So z must equal some kind of factor of the exponential j omega, right? Now here the solution of such equation, let's write it here. So what we're talking about here is that we want to solve this equation, right? The solution is in the form, this form, right? So it's z equals e to the power j 2 pi k over k over m. So what we're doing here actually is that we are taking the unit circle where z equals 1, right? and we're dividing it into m points here, right? M points in a uniform manner. Okay, right. So we have m zeros as a solution for this equation, and k is a counter from 0 to m minus 1. Okay, great. Now let's move from the transfer function to the frequency response. We substitute z by the complex exponential. We get equation 3.53, right? We do the usual tricks. We take as a common factor exponential minus j omega m by 2 to get here. This time we get a sign, right? Because we have a minus sign here. Sorry. So we have a minus sign here, right? We do the same thing in the denominator. So we get this term, right? And you can easily note that this would be the phi of omega, right? And this would be, if you take the absolute value, so it would be the absolute value. So this would be the magnitude response, and this would be the phase response, right? So we're taking the phase response here. So we get 3.56, and we said earlier, as we said earlier, this is the magnitude response. Now if we take the minus derivative of the phase response, we arrive at the group delay as we did before. Okay, now let's find the first null bandwidth. So we say that the magnitude response should be equal to 0, and this is very simple. So this term will equal to 0 when the numerator equals to 0. So the numerator, so we say when the numerator equals to 0, when the sign equals to 0, the sign equals to 0 when the argument of the sign, which is omega m by 2, must equal pi. Hence we get equation 3.59. This is the first null bandwidth. As for the minus 3 dB bandwidth, it's not as easy to find it. It can be shown that the minus 3 dB bandwidth is approximately equal to equation 3.16. Okay, let's take an example. Now the moving average filters are usually used to clean up constant values, or let's say low frequency content signals, right? So let's say that we have a sensor signal consisting of a constant value plus some interference or noise, okay? And we want to clean up the signal x of n, meaning that we want to preserve or keep A and somehow mitigate or eliminate W of n, okay? Let's study 3 cases. Let's say that we want to design a filter, of course a moving average filter with a bandwidth of pi over 6 radians. Okay, so this is the first requirement. Another different requirement, let's say that we want to remove an interference or noise of a cosine of pi over 4n. And a third case, when the interference is has a frequency of 4 pi over 3. Okay, so we want to design 3 filters, right? The first one with a specified bandwidth, the second 2 we want to eliminate a specified noise or interference. Okay, now since we did not determine the type of the bandwidth, we will try them both. So we'll first find the first 2 null bandwidth, which is you plug in the values in the formula, right? So we have the first null will be pi over 6, and use this formula here. So easily the moving average filter must have 12 points. as for the MyStreetDB case, you solve for m, right? You plug in here the MyStreetDB bound, which is pi over 6, you into this formula, and you get this value. Note that this value is not an integer, so we have to round up just to make sure that we are achieving the required bandwidth, right? Okay. For the second case, we want to eliminate this noise. As we seen earlier, the zeros are located at 2 pi k m over m. K is a counter from 0 till m minus 1. So we have m zeros. We want to put our zero of the filter at the frequency of the interference. So one of those zeros must equal pi over 4. The simple case is what? To set k equal to 1, then we have here this equation. The pi's cancel out with the pi on the other side, so and k equals to 1. Now we have 2 over m equals 1 over 4, meaning that m by 2 equals 4. Now this will give us m equals 8 points. As for the third and final case here, we want to zero out this sorry, there's a typo here, this should be 4. We want to zero out this interference, which has a frequency or angular frequency of 4 pi over 3. What we do here is, okay, we set k equal to 2, so we have 2. Now 2 by 2 is 4, and we have a pi, so pi, 4 pi here and 4 pi there, they cancel out. Okay, we're left with m equals 3 points. That's it.